Hello everybody. I want to come back and look at the functional groups that we talked about yesterday in our 3.7 note. Now, I'm going to skip from 3.7 to 3.9 because 3.9 looks at some of the groups that we were talking about. If I go back to my 3.7 note, in the 3.7 note, you see that we had all these different groups. Let me just do a little bit of erasing here, so these things don't get in the way as we're trying to work with them. Okay, so this was our chart from the textbook from 3.7, and in the chart we saw a number of different groups. Now, first off were the haloalkanes. Haloalkanes are alkanes, right? They're hydrocarbons, right, such as SCH3 here, with a halogen attached to it. Now, halogens often in chemistry get the symbol X. I'm not sure why X, but they get the symbol X. And when they get the symbol X, whenever we see an X, we typically think of it as a halogen. And we know our halogens are chlorine, fluorine, iodine, and sometimes bromine. And when these things are attached to our hydrocarbons, they become haloalkanes, halogenated alkanes, right? So I'm thinking about a hydrocarbon that has some type of halogen attached to it. Now again, if I scoot down, I'm just going to go through the list here, and then we'll go down to 3.9 and look at some of the applications of these. Our second and probably one of the most important, I shouldn't say that, these are all important, I'd say probably least important are probably the haloalkanes. We use them for a lot of things, like a crazy lot of things in chemistry, but as I was saying yesterday, they weren't here on this planet before 1950, right? So we made them, well, we discovered them, and we discovered what they could be used for, and then we made a lot of them, and then since then we've tried to stop making them because a lot of them are maybe not so good either for humans or for the planet. Some of these include chlorofluorocarbons, which are chemicals that go up in the atmosphere when they escape. They were used ages ago in air conditioning systems, and when they escape from an air conditioning system, they're gases. They're very light gases, so they float up into the upper atmosphere where they come in contact with ozone, and they chew through ozone. They destroy ozone. Well, ozone's kind of important. It protects humans from exposure to ultraviolet sun. It also protects all the other species from ultraviolet sun. So we first noticed that species like penguins at the South Pole were starting to develop skin cancer, where we'd never seen a lot of skin cancer in penguins. And we're trying to figure out what's going on. Why are they getting skin cancers or something that's affecting them? We think, well, sunlight's the only thing that really we know of that causes the number one cause of skin cancer. Maybe they're getting more sun, but they're outside, and they've always been outside, but now they're getting more skin cancer, and we realized there was a hole in the ozone layer, and that was being caused by the production of these chlorofluorocarbons, or haloalkanes, and since then most countries in the world have banned making them because they are especially bad for the ozone layer, which affects every country on the planet. So every country on the planet basically signed a pact to stop making these things. But they're used for lots of other things too, and aren't necessarily always as bad as the CFCs, the chlorofluorocarbons. A really important group are the alcohols. The alcohols have an OH group, which is called a hydroxyl group. The hydroxyl group, whenever I see that on a molecule like it is over here, right, that makes it an alcohol. And the alcohols are a massive, massive group of hydrocarbons. I would say, other than the straight hydrocarbons, alcohols are probably, in my books, the second most common and very important in biology and in chemistry and in understanding the planet. Our third group, our next, I'd say, four groups, which are ketones, aldehydes, carboxylic acids, and esters, all contain a group called a carbonyl group. The carbonyl group is a C double bond O. I talked about the structure of that yesterday. So ketones and aldehydes have a C double bond O. A ketone has the C double bond O, which is on a carbon in the middle of a chain, which means there are carbons on one side of it and carbons on the other side of it. That makes it a ketone. If the C double bond O is on the terminal carbon of the chain, that means there's just an H on the end, and that's called an aldehyde. And again, that's got its own group of hydrocarbon derivatives called aldehydes. Our third group with the carbonyl, the C double bond O, is something called a carboxyl group. The carboxyl contains the C double bond O, which we see here, but it also contains an alcohol. The two of them are both present, and together they form a structure which is called a carboxylic acid. This includes all kinds of different acids that we have in biology, like citric acid, which you find in citrus fruits, lactic acid, we talked about yesterday, ascorbic acid, which is vitamin C. So a lot of different types of biological acids are carboxylic acids, and they all contain that terminal or end carbon, which has a double bonded O, and it also has the OH alcohol group, and those two combined make the structure called a carboxylic acid. Our next group, so we've talked about these. Esters also contain the carbonyl group, but they also have an oxygen which is coupled to the carbon. That linkage, called an ester linkage, a linkage is something that holds things together. This holds together a hydrocarbon chain on this side and the hydrocarbon chain on this side. And this linkage here, C double bond O, is called an ester linkage or an ester group. And this type of hydrocarbon derivatives, again, very common in biology, very nice smelling things for the most part, and they are made by living organisms, things that smell very, very nice, often in fruits or in flowers. A lot of esters are, like I said, from plants. Now, if we keep on going here, our last two groups contain nitrogen. Those are amines and amides. The amines and amides both contain a carbon bonded to nitrogen. Here and here. The difference is the one below, I can see not only does it have a nitrogen, but it also has a carbonyl group also. And amines are not necessarily anything I would say are terrifically as common in biology as amides. Amides, I said yesterday, for biologists are the way that we form proteins in living organisms is by amide bonds. And again, the amide couples the carbon to the nitrogen, just like the amine bonds the carbon to the nitrogen. I have the carbon bonded to the nitrogen, but for the amide, I also have the carbonyl group there. All right? And notice all the molecules that we've talked about here, with the exception of the haloalkanes, all of the things that you're seeing on this page have a number of things in common. Okay, probably most importantly, let me just find a space down here to write. There's a carbon bonded to an O bonded to an H, which makes an alcohol. We have the carbon bonded to a double bonded O, which makes the carbonyl group. For aldehydes, ketones, esters, carboxylic acids, and amides all have that C double bond O. And then we have a number of structures that contain a carbon to N. Now remember from yesterday's class, the O has 6 valence electrons, so it basically wants 2 more, so it forms 2 bonds, and oxygen will always put 1 bond, 2 bonds, or here both bonds are together between carbon and oxygen. Nitrogen has 5 valence electrons, which means it needs 3 more, so it typically forms 3 bonds. It forms 3 bonds, and it can bond with carbons on both sides, or it can bond with hydrogens on both sides, or it can bond with a hydrogen on top and a carbon on the bottom. A lot of different possibilities here, but the nitrogen basically couples things together. And we're going to see the importance of CO and CNs today in our 3.8 note. Okay, so if I move down to 3.9 just for a minute, 3.9 talks about the uses for a lot of these different groups. So the first one here are the haloalkanes. Again, it says compounds containing halogens. They're used in a number of different things, including pesticides. They're used in the making of plastics, in different types of solvents, in aerosol cans, spray cans, aerosols like deodorant, like cleaning products or insect repellent. They're also used in refrigerants, chemicals that we use in our refrigerators to as part of the cooling process. And they contain, you can see one here, this is a chlorofluorocarbon. Okay, chlorofluorocarbon, and it contains the central carbon, with all of the chlorine, fluorine. Right, so it's surrounded by halogens. Right, and again, this is the one that created that huge hole in the ozone layer that you can see over on this side here. That hole right over the South Pole, right, and all of Antarctica was basically exposed to direct sunlight, and that's why we were finding all the penguins down there with with skin cancer. And it's saying even though the CFCs were once widely used, they're now banned in a lot of places. Okay, when we move down and talk about alcohols, again, this is the alcohol here that is in all of the drinking alcohols that I was talking about yesterday: rum, whiskey, vodka, gin, beer, wine. Right? All of those things contain this chemical here. This is the alcohol. It's called ethanol. I see ethane there, which means 2 carbons. So here's my ethane. And all means it's got an OH group on it. So there's ethanol. Right? And that's the compound. It's made by yeasts. Yeasts are what make the alcohol in beer, wine, and then ultimately for distilled alcoholic beverages also. So all of our alcohols contain the OH group, and again, a massive industry there too. So we got this industry up here, all these different chemicals, the pesticides, the solvents, the plastics. Down here, all the alcohols. If I move down to the aldehydes and ketones, you can see someone's preserved brain in the jar there. The chemical, which is called methanol, this one here, I'm seeing the word methane, which means 1 carbon. I'm seeing that it's an aldehyde, which means that that end carbon contains both the C double bond O and the H, makes it methanol. And this was the common one that we used to use quite often in our dissected organisms for biology. So if we were doing a dissection, a pig dissection, or a fish dissection, or even an earthworm dissection, you think, oh, that thing smells. That would have been originally the chemical called methanol, which is also called formaldehyde, and it's got a very strong smell. It smells chemically. It doesn't smell rotten. It smells like a chemical. Think about the smell of gasoline and how strong it is. Think about the smell of vinegar and how strong it is. Right? The smell of acetone and how strong it is. Right? Formaldehyde is the same. It's got a very strong, chemically unique smell, but it's an aldehyde. And the ketones are the same. They've got the C double bond O also, and a lot of them have got very distinct smells, things that are characteristic that we would recognize. And they're used for a lot of different things, again, for making plastics, for making all kinds of other chemicals, such as disinfectants, right, for killing bacteria. We've got carboxylic acids down here. We talked about the example yesterday, which is the one that's made by ants, by biting ants or stinging ants. The chemical they make is called formic acid. That's the common name. The proper scientific name for it is methanoic acid. So I see methane there, which means one carbon. And it's a carboxylic acid because it's got a C double bond O and because it's got a COH together all on that terminal carbon. Right? Those carboxylic acids, again, all kinds of things use carboxylic acids. They're talking about things that are in our food, things that are in skincare products, chemicals that we use for making soaps and detergents for cleaning. We talked about vitamin C in citrus fruits, lemons, oranges, and grapefruits containing vitamin C. Also containing citric acid, which is why they're called citric fruits or citrus fruits. And those are all carboxylic acids. Right? So again, very common in plants and in animals. If I keep moving up here, we're almost done. I've got the esters. Esters, again, produce a lot of the very sweet-smelling things. They're very biologically important. If you go on to learn a little bit of biochemistry, if you're interested in doing molecular biology or getting into biotechnology or chemical engineering technology, you'll be using a lot of these esters for different things because they're very important in biology in terms of their genetic material and in terms of a lot of the biomolecules such as the fats. But a lot of them have very, very strong smells, and a lot of them smell very nice. Right? Again, they've got the raspberries there, and again, the smell of raspberries can be really wonderful. And then the last groups contain the nitrogen, and they are the amines and amides. The example that they've shown you here is acetaminophen or Tylenol. And acetaminophen, again, has got the C double bonded O, and the carbon is also bonded to a nitrogen. So that makes it an amide. And the amides, again, are used for a lot of things. The amines are often used, again, in solvents. They're used for fertilizers. They're used for some of the artificial sweeteners that you might see in diet foods when they're trying to sweeten things without sugar. A lot of those things are amines, right? So, again, lots and lots of places where these different functional groups are showing up in organic chemistry. So really, if you go all the way back to that chart, okay, this chart here, I would encourage you to have this chart handy when it comes time to writing the test for this unit on organic. You probably want to have this page open because it tells you a lot about the chemical structure of the different hydrocarbon derivatives of the families, right? Hydrocarbon derivatives or families. And what their chemical structure is, and then below that in 3.9, what they're often were some of their uses, not what they're often used for, but what some of their uses are. Now, our last note in chapter 3 here talks about those functional groups that we were just talking about, the CO bonds and the C double bond O bonds, and the carbon halogen bonds like the one I've got over here. Now, one of the things that we're talking about here, when I'm talking about elements and organic chemistry, I'm talking about carbon-hydrogen bonds, I'm talking about carbon-oxygen bonds, I'm talking about oxygen-hydrogen bonds, I'm talking about carbon-oxygen double bonds, I'm talking about carbon-carbon bonds, and carbon-nitrogen bonds, and nitrogen-hydrogen bonds. Okay, this is everything that we've talked about. Oh, and carbon halogens, where a halogen I'm just going to call X, whether it's chlorine, bromine, iodine, or fluorine. But again, less important biologically. And since I teach more biology these days than anything else, I'm going to talk largely about these molecules up here. So when I look at these, I say, what do all of these have in common? Well, on that entire list up here, right, this entire list, there are no metals. These are all nonmetals. And we know that when a nonmetal is bonded to a nonmetal, they share electrons, right? They're covalent bonds. So when carbon bonds to hydrogen, right here, carbon bonds to hydrogen. The carbon's a nonmetal, hydrogen's a nonmetal, so it's a covalent bond. They share electrons. Okay, carbon, oxygen, nonmetal, nonmetal. They will share electrons. Covalent bond, covalent bond, covalent bond. All of them are all covalent bonds. Now, it's important for us to recognize at this point in time that there are two kinds of covalent bonds. Right? Covalent bonds are broken down into either polar covalent bonds or non-polar covalent bonds. Now, when I think about poles, if I think about the planet, right, the planet Earth, North Pole, South Pole, we just saw that picture of the South Pole a moment ago. Poles are opposites, right? The opposite of the North Pole is the South Pole. So when we talk about polar covalent bonds, we're talking about a bond that has two opposite ends. Nonpolar means that they're not polar, they're the same on both ends. Now, what this has to do with is the fact that when atoms are sharing electrons, they don't always share equally. Now, let's say you decided you wanted to share a plate of fries in the cafeteria with somebody, or you ordered a pizza and you're going to split a pizza with somebody. You say, yeah, we're going to share this pizza, and there are 8 slices in this pizza. Next thing you know, one person got 5 slices and one person got 3 slices. Right? And you think, well, if you're an outsider looking in, you say, well, one guy here obviously got ripped off. If you're the person who are getting the 5 and 3, you might say, that's okay, I really only wanted 3 pieces. I can only eat 3. The other person says, I'm starving, I could easily eat 5 pieces. And you both leave kind of feeling okay about it. But from the outsider looking in, you're saying one of those people got ripped off here. Right? One got more than their share. And that's what happens in a polar covalent bond. When two atoms are sharing the electrons, one of the atoms has a stronger pull on those electrons, and when they're sharing, the electrons spend more of their time closer to that atom. So here's an example over here of carbon bonded to chlorine. Okay, so a haloalkane. Now it turns out when carbon and chlorine, nonmetal and nonmetal, when they get together to form a bond, they share electrons. Carbon puts in an electron, chlorine puts in an electron, and they share the pair. However, chlorine has a much stronger pull on those electrons. So instead of the 2 electrons sitting here in the middle between the 2 atoms, the chlorine has such a strong pull that what it's going to do is it's going to pull the electrons closer to itself. Right? So in this space here between the carbon and the chlorine nuclei, the electrons are closer to the chlorine side. Now remember, here they're drawn as solid balls, solid spheres. But in reality, this is space, right? This is empty space between one nucleus on this side and one nucleus on the other side. And what's ultimately happening is this nucleus here has the greater pull. The chlorine side has the greater pull, and what it's going to do is it's going to pull the electrons this way towards itself. What that means is in that space between carbon and chlorine, you can see I've got a little funny symbol here which is called a small delta. In math, we sometimes learn about the symbol delta, right? Just like we learn about alpha and beta and pi, right? We also learn about delta here, and that's the capital D in the Latin alphabet. And there's a lowercase d, which is this little d, which kind of looks like our little d. And it's got a negative sign if it's a delta negative, or a little positive sign beside it, if it's a delta positive. Okay, and what you can see down here is that the chlorine end of that bond is delta positive, and the carbon end is delta positive and the chlorine end is delta negative. What the delta talks about is a small part charge, which means even though carbon and chlorine are sharing the electrons, electrons are pulled towards the chlorine, which means in the space between carbon and chlorine, it's a little more negative on this side because chlorine has a stronger pull, and it's a little more positive on this side because the carbon has less pull on the electrons. So in the space here, there's slightly negative on the chlorine side and slightly positive on the carbon side. Okay, those are partial charges. So down here, you can see that it says one end of the carbon-chlorine bond is partially negative, delta negative. The other end is partially positive, delta positive, and the arrow points in the direction where the electrons spend more time. Right? The more negative side, because of the electrons, we call that the electronegative side. Now, question should be coming up for you now as to how do I know whether the electrons are going to get pulled towards carbon or towards chlorine, right? Where's the deciding factor here? Well, it turns out that on our periodic table, if we look, we'll often see in our boxes on the periodic table the electronegativity. Now, I don't know if I've got a periodic table on my iPad here. Let me see for a moment. Okay, I'm going to detour here for a moment and see if I can just quickly pull up a periodic table. Now, when I look at a periodic table of the elements, okay, this one doesn't have electronegativities. Hang on a minute. Let me see if I can find a periodic table that does have electronegativities. Now, ours does, but I haven't got ours. So this one does. No, it doesn't. No, it doesn't. Hang on 1 minute. Now, on our periodic table, well, none of these have electronegativities. That's actually, I find that quite strange because it's a very common property. It's a property that we use very, very often. No, and none of these are going to all prove me wrong here. So I'm going to keep hunting because I need to find one that's got them on here. If we are going to talk about electronegativity, we need to know that each of these elements has an electronegativity associated with it. Well, sorry, I should have uploaded mine. I didn't think this was going to be hard to find one. Periodic table of elements with electronegativity. Okay, so let's see if I can pull. If it's not totally blurred out. Of course. Let's try a different one. Okay, I don't know if I like this one too much, but it'll do. Okay, so when I look at these elements, so in the helium box, or the oxygen box, what do I know about, let's say, carbon or oxygen? I know that carbon has an atomic mass of 12.01. So it's number 6 on the periodic table. It has a mass of 12.01, and it has an electronegativity of 2.55. That's what the element carbon is. Nitrogen is number 7 on the periodic table. It's N. It's got a mass of 14.01 grams per mole, and it has an electronegativity of 3.04. So on our periodic table that we have for our course, all the elements have an electronegativity right in the box. This isn't a great periodic table because it doesn't have masses. Oxygen is number 8 on the periodic table. It has a mass of 16.00, as you probably remember, and it has an electronegativity of 3.44. Okay, fluorine is up here. It's 3.98. It's the highest electronegativity on the periodic table. Okay, so when I'm looking at the periodic table now, I can see that different elements have different attractions for electrons, except the halogens here. Now these ones down here are a little bit of an exception, but these ones have no attraction for electrons because they are noble gases. They don't attract electrons. So there should be no data available for how they attract electrons because ultimately they don't attract electrons. So there's that number called electronegativity. So the electronegativity is in the box for each element. Okay, so if I was to look at our periodic table, I would see fluorine. On that one periodic table, it was 3.95, but if we just round it, it rounds to 4.0. So if there's fluorine, chlorine is 3.2, carbon is 2.6, oxygen is 3.4, nitrogen, and hydrogen. Okay, so those are the elements I was just talking about a moment ago when I'm saying these are the elements that we typically find in most of our covalent molecules, our molecular molecules in organic chemistry. Now, if I've got two atoms sharing electrons, let's say carbon and chlorine. So I've got carbon sharing one of its electrons with chlorine. Okay, chlorine has 7 electrons. It's a halogen, so it has 7 electrons. There's its 7. And it's going to share its 7th electron with carbon, which shares one of its 4 back with chlorine. Okay, so there's my pair of electrons, there's my covalent bond. Now when I look at the electronegativities, I can see chlorine is 3.2 and carbon is 2.6. Chlorine is higher, it has a higher attraction for electrons, so those electrons that are in there, so let's just erase that and let's just replace it with a covalent bond. There's my covalent bond. But I know that now that it's a polar covalent bond and that the electrons that are in that space are closer to chlorine. So in this space here, the chlorine side is more negative and the carbon side is more positive. So we draw a little arrow in there, which is not very clear there. We draw a little arrow in to show that the electrons are pulled towards chlorine. If I go back to my textbook there, we just saw that in the picture, whoops, where the carbon and the chlorine are sharing the pair of electrons in here, right? And as they share that pair of electrons, the electrons in here get pulled towards chlorine. You can see the arrow there is pointing towards chlorine to say the electrons spend more time closer to chlorine, less time towards carbon. That means the chlorine end of that space is more negative, and the carbon end of that space is less negative or more positive. Okay, so we actually denote the where the electrons are spending their time by using the little arrow there to show where the electrons are going to be. So there's carbon at 2.6 and oxygen was 3.4. Again, let me go back to my note. So carbon is 2.6, oxygen's 3.4. So when I look at how they share those electrons, so carbon and oxygen, which is right here, right? I'm going to take the difference, the delta here, so there's two deltas, right? There's the capital D delta, which is the big triangle, and the little delta, which is the little d, which is that funny shape. This is capital delta, and this is the lowercase delta, right? So it looks a bit like a backwards letter, like a letter D in our alphabet, except it's kind of a little more curved at the top and a little more curved at the bottom. And then typically with the little delta, it's either delta negative or delta positive, depending on which end of the polar bond we're talking about. So when I look at delta En down here, between carbon and oxygen, so carbon and oxygen are sharing a bond, are sharing a pair of electrons, I'm going to look at the difference between their electronegativities. So oxygen is the higher one, right? Oxygen up here is 3.4, and carbon up here is 2.6. So I'm going to take my 3.4 and subtract from it the lower number, 2.6, and the answer turns out to be 0.8. That's called delta En, or the difference in electronegativity. That's what the delta means, difference. If I've got two carbon bonds, two carbons that are bonded together, the carbon on one side and the carbon on the other, because what we've been talking about for the last 2 days is carbon-carbon bonds. Carbon is 2.6, as we can see here. Carbon is 2.6 here. Carbon is 2.6 here, which means there's no difference between their electronegativities. The delta En is 0 because one carbon is 2.6, the other atom is 2.6, and ultimately there's no difference, so there's no polarity, right? That's called a non-polar bond. When carbon bonds to hydrogen, so again, we've been talking about CH2, CH3, CH2, CH3. When I'm looking at these carbon-hydrogen bonds, when I look at the carbon-hydrogen bonds, carbon we see is 2.6 up here, and hydrogen is 2.2. So if I look at the difference in their electronegativity for carbon and hydrogen, it's 2.6 minus 2.2, which is 0.4. So that's the goal here, is to measure, calculate the delta En, the difference in the electronegativity of the two atoms. If oxygen is bonded to hydrogen, like we have in alcohols, all these OH groups, notice that oxygen up here is 3.4, hydrogen is 2.2. So if I take my 3.4 less the 2.2 of hydrogen, I get 1.2, and that tells me the oxygen is pulling the electrons closer to itself, away from the hydrogen. Right, so what do these numbers mean? 0, 0.4, 0.8, 1.2. Right? What do these numbers tell me? Well, they tell me how polar that bond is. So remember I said earlier that there are two kinds of covalent bonds. The covalent bonds that are polar and covalent bonds that are non-polar. So, the last one I want to talk about is a nitrogen-hydrogen bond, because again, it's a pretty common one also. And if I look at nitrogen, which is 3.0, and hydrogen, which is 2.2, the difference between nitrogen and hydrogen is 0.8. Now, when we're trying to decide what those numbers mean, there's a couple of numbers. So again, if I'm talking about pH and I say, what's the magic number for pH? You'd say, well, it's 7, right? 7 is an important number in pH because 7 means it's neutral. pH 0 is very acidic. pH 14 is really basic. But we know a couple of those important numbers. In electronegativity, the important numbers are 0.4, and 1.7. Okay, those are the two important numbers. And again, you'll probably need to know those two numbers. So when I'm looking at the delta En, if the delta En is 0.4 or less, that means there's not much difference in the electronegativities. Most of the electrons that are in there stay in the middle. They're not pulled to one end or the other, so there's no polarity. There's no positive and negative end. This is called a nonpolar covalent bond. Right? Nonpolar shared covalent bond. If the difference in electronegativity is higher than 0.4, between 0.4 and 1.7, then the one that's higher, whichever element has the higher electronegativity, will pull the electrons towards itself, making that end more negative. And the one that is losing the battle with the lower electronegativity, it gets the positive end of that space. So now I have a space that is positive and negative. In other words, it's polar. And if it's polar, right, if it's a polar covalent bond, then we know that one end is positive and one end is negative. Okay, so this is a really important concept in looking at these functional groups because they help me to understand how these molecules are going to behave in terms of their physical properties. The physical properties include how well will this chemical dissolve in water? What is going to be the melting and boiling points of this chemical? Is it going to be a solid, liquid, or gas? That type of thing. So all of that information comes from looking at the molecule and looking at the bonds that we have using these elements here, right? So because these are the elements, the nonmetals that we have in organic chemistry, then they're the ones that we're largely going to be using when we try to decide, is a covalent bond going to be polar or nonpolar? Now, let me go back to the textbook for a minute here. So this is all kind of a lot to grasp. The textbook does a really good job of explaining this. So after you're done listening to me talk about electronegativity and delta electronegativity, delta En, go back to the textbook and read out the couple of pages, the 2 pages, page 112 and 113, that talk about electronegativity. So those are all the electronegativity values there. And the little mini activity here is asking you to predict whether a bond is going to be polar covalent or polar non-covalent. Polar covalent or non-polar covalent. And again, you're just going to look at the delta En, the difference in electronegativity, and see if the number is higher, is between 0, it should be between 0 and 0.4. Means the electrons are being shared, or if it's 0.5 to 1.7, then it's going to be polar covalent. One atom has a stronger pull on the electrons than the other. Okay, well, what happens if it's 1.9? Is that even possible? Well, sure, it's possible. If I look at elements like sodium and chlorine, and I look at their delta En, you think, well, hang on, sodium's a metal, chlorine's a non-metal, so chlorine is going to steal the electron from sodium because the metals have one valence electron, like sodium, and it wants to get rid of it. And chlorine has 7 valence electrons, and it really wants an electron, so it's going to steal an electron from sodium. If the delta En is greater than 1.7, it's going to be an ionic bond, right? Because the pull of the one element is so much higher than the other one that it's just going to rip the electron off from the other elements, and I'm going to end up making a charged, in other words, an ion, a charged atom, and which is negative, and the one that's losing its electron is going to become positive. Okay, so those are polar bonds and non-polar bonds. Now, the last piece here that talks about the properties, the physical properties of organic compounds, is this new type of bonding that we're going to talk about just in passing, called hydrogen bonding. Hydrogen bonding happens between typically typically molecules that have got alcohols and or carbonyl groups, the C double bond O's. So if I look at this, let's make this bigger here. Okay, so here's my molecule CH3OH. Okay, so it's methane. It's got one carbon and it's got an OH group, alcohol, so that's called methanol. And there it is in my beaker. Oh, but there's more than one in the beaker. Here's another one in the beaker. And here's another one in the beaker. And here's another one in the beaker, because my beaker is filled with these things. Now it turns out that when these things are all floating around in the beaker, notice one thing that we have identified here is oxygen has a higher electronegativity than hydrogen. Right? Oxygen is 3.4, hydrogen is 2.2. Oxygen is 3.4, hydrogen is 2.2. So if I look at the difference in electronegativities, 3.4 minus 2.2, it's 1.2, right, which is greater than 0.4, which means the higher one, which is oxygen, is going to pull the electrons here, let me get rid of that, pull the electrons in this bond here. They're going to get pulled towards the oxygen end, meaning the oxygen end becomes slightly negative and the hydrogen end of this becomes slightly positive. Oh, but in the other methanol beside it, the oxygen is negative and the hydrogen is positive. And in the next methanol down here, the oxygen is negative and the hydrogen is positive. Hopefully you're getting the idea here that in all of these molecules, the oxygen is negative and the hydrogen is positive, because the oxygen is 3.4, the hydrogen is only 2.2, so the oxygen wins the battle, and the oxygen will always be negative. Now, notice what I've got in this beaker now is I've got some negative oxygens and some positive hydrogens on neighboring molecules. So the oxygen on this molecule here will be attracted, which is negative, will be attracted to the positive hydrogen on this next molecule. And the oxygen on that next molecule sees the positive hydrogen of this molecule, and it's attracted to this positive. And this negative oxygen here sees the positive on that hydrogen, and it's attracted. And the negative oxygen sees the hydrogen here, and it's attracted. So notice that it's not a strong attraction. It's not enough to rip hydrogens off molecules, but it's just kind of a weak attraction. It's kind of like that balloon that's stuck to the wall after you've rubbed it in your hair. Right? It's a pretty weak force of attraction. If a wind blew past it, it would blow the balloon off the wall. But it's strong enough to hold that balloon up there. This is the same thing. It's a weak interaction between the negative on one particle and the positive on the next molecule. Okay? That's called hydrogen bonding. It happens between the hydrogen on one atom and the oxygen on a neighboring molecule. So let's try and get this back down to size here. So you can see that this hydrogen bonding happens pretty often. And what that does is it means the molecules are attracted to each other and they hold on to each other tighter, which means instead of having a really low boiling point, because they're holding on to their neighbors stronger, I have to add more energy to make them boil. And because of that, they have higher boiling points. Right? I've got to heat them more to make them boil. So if I've got a molecule like CH4, it boils at around minus 100 or something. And if I've got a molecule which is CH3OH, it boils at around 60 degrees Celsius. There's almost 150 degrees difference in the boiling points by taking this oxygen right here, right? Notice that they both are CH4. The difference is this one has the O in it, which means I've now got an OH bond, which makes for a positive H and a negative O, and now these hold on to their neighbors. And where this is a gas at room temperature, this is a liquid at room temperature, because this one boils, the top one, the methane here, this one here, boils at like 100 below zero. Right? It doesn't take much energy to boil that because they're not holding on to their neighbors. These hold on to their neighbors, which means I've got to heat them a lot more in order for them to boil. The other thing that happens is these molecules here also, so let me just erase some of this stuff here. If I put these molecules in water, so if I put these in water, here's an H2O, let me erase this here too. If I put this molecule in water, here's the molecule here, and here's my water, HOH, water. And again, notice that in an OH bond, like we're talking about up here, oxygen is going to pull the electrons towards itself. So in this OH bond here, the oxygen is going to pull the electrons towards itself, meaning this side becomes negative and this side becomes partially positive. Delta negative, delta positive. And in this OH bond on this side of water, the oxygen becomes slightly negative and the hydrogen becomes positive. Because again, remember, the oxygen is 3.4 and the hydrogen's only 2.2. So even in water, water has a negative oxygen and a positive hydrogen. But when I put this molecule now in water, put a drop in water, the oxygen on the methanol here, which is negative, sees the positive H of water and it says, aha, opposites attract. And the hydrogen on the methanol sees the positive, the positive hydrogen sees the negative oxygen, and same thing, opposites attract. And opposites, O's, attract to H's. Now, what that means is methanol dissolves very well in water. It likes water. It's attracted to water and it will dissolve in water. If I put a molecule, now methane, CH4, is already a gas. But if I tried to get it to dissolve in water, it's not going to happen. And the reason why it's not going to happen, just let me go to my whiteboard here for a minute. The reason why it's not going to happen is because if I have the difference between carbon and hydrogen is only 0.4, which means all of these bonds are non-polar. There's no positive end and no negative end. So when I put this in water, when I put this in water, you think, oh, the negative O should be attracted to the positive H. Oh, except there is no positive H. This H is not positive. That means this attraction doesn't happen. This molecule doesn't like water, right? And it will not dissolve in water. So when I think some things dissolve in water and some things won't dissolve in water, the things that dissolve in water are things like ionic compounds that have charge on them, because the charge will interact with the positive H's on water and the negative O's on water. But molecules like fats, again, if you try and do dishes or try and clean a bad stain off your pants or your shirt or something, and you've got a bad stain on there, say a grass stain, you want to get it off, it's not going to come off because it's hydrophobic. It's a molecule that doesn't like water, and it will not dissolve in water because there are no polar bonds. So when I've got polar bonds, which comes back to electronegativity, if I've got polar bonds, it will change the way the molecules interact with water. Polar molecules dissolve in water because water is polar. Non-polar molecules will not dissolve in water. Like dissolves like. So if I've got a non-polar solvent, I can dissolve methane because it's non-polar. If I've got a polar solvent, it won't dissolve methane. It won't dissolve methane because methane is nonpolar. So I can dissolve polar things in polar solvents or nonpolar things, chemicals, in nonpolar solvents, but I can't get polar to dissolve in nonpolar. So if I go back to my final note here, right, when I'm looking at this concept of electronegativity, electronegativity changes the physical properties of the functional groups change the polarity of molecules, and then the polarity decides whether it's going to dissolve in water or not, and what is it going to be at room temperature, a solid, liquid, or a gas, based upon the amount of hydrogen bonding between molecules and their neighbors. So like I said, this is really probably the most complicated thing we're going to talk about in organic chemistry. Take some time and read through those 2 pages in your textbook. 112 to 113. And then if I look at the end of the chapter, we're basically done all of chapter 3 now. So I'm going to leave you with the questions on page 117. So let me go back to my note. I'm going to leave you with the questions on page 117, questions 1 to 11. Come on. Page 117. And then if I look at our calendar for next week, I can see that we are Unit 4, Chapter 3. We're going to have a review period for Chapter 3 on Monday. Now, Chapter 4 is actually a pretty short chapter, and we've only spent a week or so on Chapter 3. So I'm going to have a test on both Chapters 3 and 4 together because they're both short. Chapter 4 we should be able to do in probably 3 days. So on Monday of next week, we are going to spend the period. I'm not going to produce any more notes for Chapter 3 because that's the end. I will leave you with the review here on page 125 to work on from our textbook. And then on Tuesday we'll have a live class. And if you have any questions, I'll probably go over all of this organic we've been doing. I'll go over functional groups. I'll go over naming and drawing structure of organic compounds. And then I will take up some of this review. Maybe before then, I might even post the answers to this in a video, maybe on the weekend ahead of next week. Okay, so over the weekend, maybe try and work on some of that review. Notice that our career assignment for Unit 4 is due on Monday. We're almost done, right? We've got the career for Unit 4, and then after that, we have one more STSE and one more career assignment. By June 1st, we're done all the assignments, right? And you'll be in great shape. So we've done the ISU, we've done 5 career assignments, and we've done 5 STSE assignments. You guys have done a lot of work. So